Well, it's just gone 12 o'clock, so good afternoon and welcome everyone to our third Lunch and Learn session, reflecting on the many uses of the link float pontoon system. This afternoon, we're going to cover the use of the system to provide floating bridging. I'm Steve Marshall, Director at VolkerMarine Specialist Businesses and responsible for the VolkerMarine Services operations across the UK. Today, I'm joined by Chris Shorrock, Marine Technical Manager at VolkerMarine Services. We also have Hamish Adamson, MD at Harland Solutions, and we've got Dr. Cliff Hall, Divisional Team Leader at Mott MacDonald. So we can have the next slide, please, Natalie. So a few small rules when we're taking part in the Lunch and Learn session. So if you can mute your microphone when you're not talking, if possible, please turn on your video when you are speaking. This call will be recorded and will be available at the end of the session for those who wish to see a copy. If you have a question, you can post that in the chat bar, or you can raise your hand in the comments. Remember to unmute when you want to talk. It's always a good idea. And then this is an open forum. Everyone is equal, so please be respectful. And please share the knowledge from the session with your colleagues. So this afternoon, we'll discuss the use of the link float pontoon system and how it can be used to provide a number of solutions for providing access across water. So I'm going to cover the history of the unit and previous uses. Chris is going to pick up typical construction plant crossings, load capacity, general arrangements, and show some examples of the work we've carried out in the past. Hamish is going to provide an overview of a current project that we have on the ground, providing an access road across a pontoon, a canal. And then Dr. Cliff is going to talk about Canary Wharf, which is a project we provided a couple of years ago, which provided a 120-ton capacity roadway and load-out platform for a contractor in central London. And then we'll finish off the session with a question and answer session. So, pontoons have been used as a way of crossing water courses for millennia. There are many references in Roman, Persian, and Chinese history to the use of such structures. Modern modular or unit construction pontoon systems were developed during the Second World War, with the unifloat and link float concepts stemming from trials and experiments at the Military Engineering Experimental Establishment, or MEXI, in Dorset. The military brief was to provide a road transportable pontoon system that would be capable of being carried on a 3.5-ton truck. Each unit was required to support 10 tons and be watertight and could be connected in the water. The units were also to be used to support Bailey bridging units as floating piers. So we've been involved with the link float concept since the 1980s, and we've been manufacturing ourselves in Morecambe since 2000. Next slide, please. So the link float system complies with all of the MEXI requirements. Each standard unit is 3.5 tons. It has 3 watertight compartments, and it incorporates an innovative gunnel system that allows easy connection to bridging systems such as the Bailey Bridge or maybe bridge sections. It can connect with winches, handrails, mats, bollards, ladders, fair leads. The system includes nearly 200 accessories, such as spud legs, spud pontoons, ramps, scow ends, spacer frames, and many more. And it really mirrors a Meccano set in the simplicity and the ease of constructability. In the top photograph, you can see a British Chieftain main battle tank of 55 tons crossing a complete link float bridge on an exercise. The deck is protected with timber mats, which assist in spreading the load from the tracks of the tank over the pontoon, and they protect the steelwork. You can see where the bridge has been split into individual sections using hinged interconnectors, and these are used to reduce the moment transfer between pontoons. As you can see, this bridge is entirely link float pontoons, and basically formed of a number of floating rafts connected by the interconnectors. In the lower bridge, we can see the Demerara Bridge crossing in Georgetown, Guyana. Now, this is a toll bridge which spans 1,850 meters across the harbour and includes a raised section for small vessels to pass, together with a retractable section to allow bulk carriers to access the harbour. The bridge was constructed in 10 months and was reputably the world's longest floating bridge when completed in 1978. The bridge is still in use, I believe, to this day, and it's made up of unifloat pontoons forming floating piers and Bailey Bridge sections spanning between the piers. Next slide, please, Natalie. So now we're going to hand over to Chris, who's going to talk about the system capabilities and show some further examples of bridging we have provided using the link float.
Okay, good afternoon. This is the North Pilfrey Bridge in Lincolnshire, which was constructed in 2012. As part of the construction, there was a requirement to get construction traffic across the canal. Volker Brooks, as it was then, was tasked by Balfour Beatty with the design, hire, installation and eventual removal of the swing bridge. The bridge was constructed of standard 4-foot deep pontoons with timber mats on to spread the loadings. The edge protection consisted of standard link float stanchions bolted to the gunnels with tube and clamp railings. The swing mechanism on this was created by inserting a short spud leg through a side-mounted frame, which if you look at the bottom photo, you can see it on the right-hand bottom side of the pontoon. So the bridge was originally designed to be open and closed with winches, but because there was a boat permanently on site, that ended up that the boat would operate that bridge, allowing the canal to be navigable at all times. Next slide, please, Natalie. So just looking at some deck loadings, the standard link float pontoons of a 5mm deck plate consist of 5mm deck plates. These plates are supported on cross beams at approximately 600mm centres to enable loads to be transferred into the pontoon structure. The drawing bottom left shows the centre frame which runs the full length of the pontoon, and you can see the 600mm spacing on that. And the top left shows the centre frame dotted running the full length and 6 beams running across the width of the pontoon, again dotted on it, plus 2 watertight bulkheads, which are the solid lines running across the pontoon, giving the 3 individual compartments. With this structure, the pontoons are capable of accepting distributed loads, but not significant point loads. Heavy point loads should be distributed by beams resting on the gunnels to transfer the load into the structure. Designed to military load class 40, maximum wheel load 75.5 kilonewtons or 144 kilonewtons for single axle. But with timber decking to distribute the load, the wheel loads increased to 112 kilonewtons or distributed track loads to military class 80 of 8.7 newtons per centimetre squared. Next slide, please, Natalie. This was a concept design that we looked at fairly recently, which never actually became a job. But it's a similar concept to the Bailey Bridge with pontoon piers. Things that we had to consider: had to be capable of low loaders, 76-ton gross weight, 4 axle rigids up to 50 tons gross weight, and 6 axle arctics up to 54-ton gross weight. It was going to be a permanent crossing as there was no traffic in the river at that point, but it was flash flowing. That was the reason that we split the pontoons so as not to restrict the flow. And we also introduced scows on the upstream end of the pontoons to help deflect the water. And as you can see, it's basically 3 link span sections that sit on 2 pivot plates, which are central on the pontoons, which are the brown sections in the middle of the pontoon, and then moored in position with 4 spud legs. And next slide, please, Natalie. I've added this one in. Whilst not a bridge or a roadway, I see it as a bit of a hybrid. The bottom 2 pictures show the Thursday Squirrel. This is a barge operating in Poole Harbour to service the BP facility. It consists of 20 standard link float pontoons that we supplied to replace the original Unifloat pontoons. It's fitted with scow units and 3 Hydromaster propulsion units, which you can see across the back end. And the top right drawing is really a scaled down version of this Thursday Squirrel. And we supplied 9 standard pontoons last year for this. This vessel is called Vodka 3 and again is now operating in Poole Harbour, bringing timber off Brownsea Island and taking aggregate out to the island utilising tractor trailers. Next slide, please. So it's at this point that I then hand over to Hamish, who'll talk through the design and design considerations for the public access road diversion on the Grand Union Canal. And then this will be followed by Cliff, who'll talk Canary Wharf. Next slide, please. Steve, I've got a feeling that Hamish isn't on the call for some reason.
You just want to talk through the slides then, Chris?
I can. I've not rehearsed them.
Yeah, no, that'll be fine.
So this is just a bit about Harland. They're a team of naval architects, marine engineers and shipping specialists. They work on complex transport, heavy lift challenges, and they do a lot of support with us where we're looking at floating temporary structures. Okay, next slide, please. When floating, changes in weight result in changes in displacement, heel, trim, everything that must be considered. You know, the slightest movement of weight can make a big difference to how the pontoon's going to sit, etc. And again, every time a crane or truck or something goes onto a pontoon, there will be changes of hydrostatics on that system. And we need to consider things like loss of buoyancy, changes in displacement, heel, trim. Next slide, please. So this is the floating roadway that we designed for the Grand Union Canal. We had to divert an access track around onto the pontoons and then back off. Had to be suitable for pedestrian traffic and also light trucks and cars up to 3 tons in weight. So we had to consider everything as far as safety, the link floats, driving on, obviously the weight coming on the pontoon, how everything was going to react. On the picture, you can see the mooring arm. So there was a steel structure that we welded to the pontoon, and that slides up and down on the I-beam, and there's 2 of those to hold it in place. One of the other considerations that we had to look at on this project was if it was to get hit by a boat, which potentially could be up to 80 tons, would it fail, etc. There was potential, we didn't over-engineer it, and there was potential if it got hit by an 80-ton vessel that there could be failure on the mooring arms. So you'll see on the ground there is heavy breakaway chains that would actually hold back and hold the pontoons in place if there was a failure. Next slide, please, Natalie. So these are just views of the pontoon. So it was 15 link float pontoons. We had wood mats and then steel deck plates because we had the gunnels. So we had the wood, and then on top of that we had steel deck plates that were actually riveted down onto the gunnels. And then we had 2 link spans coming onto the pontoon and off the pontoon. One of the things that we spent quite a lot of time looking at was the weight of items and the size of items, so that, you know, we could fabricate everything in the Morecambe yard, pre-fitted all, so that when we got to site it could just be installed. So the link spans are actually in 2 sections, split down the center, so they'll go on a standard Arctic without being a wide load. So everything was just standard Arctics that were delivered to site, and weights were minimized so we could minimize the size of the crane. The other consideration was the canal wall. There was a restriction that we couldn't do anything. We couldn't touch the ground within 2 meters of the canal wall. So you'll see the mooring arms, the piles for the mooring arms are set back 2 meters, and there's 2 slabs for the link spans. Again, they're both set back at least 2 meters from the wall. The other thing was that the canal here was probably about 1 meter deep, but there had been an incident the year before where a sequence of events had led to the gates being left open and the actual canal had actually drained. So we had to consider that that was a potential that could happen. So the mooring arms went right down the face of the canal wall, so that if it drained, the pontoons would sit on the bottom, and off the mooring arms, sort of going back to the link spans, you can see I-beams off the triangle. They're actually catch beams, so that if the pontoon drops low, they would actually catch the ramps to stop them banging onto the wall of the canal. Next slide, please. So these are just some shots of the different bits and pieces. The bottom left-hand one is actually coming down off one of the ramps onto the pontoon. So the actual ramps at the bottom are sort of swaged out, because obviously with the movement and that, you can't, it's not just a square link float, link span, so you've got to be able to get traffic to come round. So there was a lot of restrictions there. The top left, you can see the join down the center of the 2 link spans. And the bottom right, again, the mooring arm and chains, which we've seen. Okay, next slide, please. Again, just more shots of the setup. The one on the left-hand side shows the top of the link span, and there was concrete slabs that were left over from construction, so it's bolted and hinged at that point into the concrete slab, so resin anchors into the concrete slab. And then on the other end, down on the pontoon, there's actually rubbing strips there on top of the plates, so that they slide back and forwards on the pontoons. Next slide, please, Natalie. And at this point, I hand over to Cliff, who hopefully is on the call.
Yes, thank you, Chris.
Thanks, Cliff.
Thank you, Chris. I'm Cliff Hall. I'm the Maritime Divisional Team Lead in the north of England for Mott MacDonald. Next slide, please. So this is the Canary Wharf Floating Road project for Volker Brooks, so now VolkerMarine Services. So a quick overview of the location and the time. So this is about 6 years ago. Was the execution of the project, but the start of it really from concept design moving into detailed design was some 8 years ago. So this was a project put in place to enable the construction of the Newfoundland building. So you can see that in Canary Wharf in the heart of London, in the city. And in red there on the left-hand side, you can see the floating road, so the footprint of the floating road. So this was constructed inside one of the old dock areas in Canary Wharf, and on the right-hand side you can see what it looked like during operation, really. So you can see the floating road in the dock, almost completely filling that middle dock there, that part of the middle dock, and just to the left of it the Newfoundland building under construction. Next slide, please. So just want to speak at a relatively high level about these modular pontoons, the specific use for the floating road, a little bit about strength of the units, connections and the design of the pontoon with respect to the strength of the connections, articulation. I think that's already been mentioned by Chris as a good way to assist in let's say utilizing these pontoons for heavier loads. A little bit about the road deck units, which are similar in makeup to what Chris was already been describing. Something about restraints, and then finally the link spans, gangways, ramps, if you like that were designed. Specific aspects being the torsion and the flexibility of those units, as well as the dimensions and the slope angles and so on, the gradients that were designed for. Just while this slide is still up, on the right-hand side, you can see a good overview of this floating road. So starting from the top of that photograph, you have a link span ramp coming down onto the road deck units, which you can see a kind of asphaltic type surfacing, and just where that approximately where that person is standing in the high vis yellow, you can see an articulation down the center of the road, of the floating road, and then closer to the let's see, to the bottom right, you can see another link span ramp leading up off of the road. And so the basic idea that this floating road would allow traffic to come from the right-hand side of the photo on down onto the road for then lorries to be unloaded while they were stopped on the road in the sort of two white demarcated areas, and then for those lorries to drive off the off ramp, which is again up the page on the top of that photo. So next slide, please. So around strength, articulation, and the road deck units. So this is a Tekla model. So 3D model produced by Volker Brooks, VolkerMarine Services now. You can see just a cartoon indication of one of the HGVs that it would have been designed for in terms of the loading. And now without any articulation, in the top right, you can see you have a relatively high point load in the center, and then the support of the pontoons, relatively shallow depth for this span. There's overall length of about 80 meters for this floating road, and an overall structural depth of the pontoons of about 1.2 meters. So that's quite a large span to depth ratio. You end up with quite a large sagging moment in the center of your beam. Now, a handy way to assist in still creating the same length of road, but to allow to dissipate those bending moments is to put an articulation in. To be fair, on the analysis front, that complicates things greatly and makes it a bit harder to actually use standard, let's say, software packages that you might have for naval architecture analysis of boats or so on. Oftentimes, they don't have hinges in them. So to be fair, it makes it a little bit more complicated, but it definitely helps in the physical world of relieving those stresses. Next slide, please. Similarly, if you imagine the two ramps being loaded by HGVs, one of them coming on, one of them off, you can end up with a very large hogging moment. And again, the articulation in the center does a great deal to relieving those bending moments, although it does, let's say, make the pontoon a little more flexible and it does move around a little bit more, deflect more. Next slide, thanks. Restraints. Now, for this project, similar issues as what Chris was mentioning for the earlier project, but basically some aspects of the dock in which it is being in which it was assembled are such that the dock walls themselves were listed structures, and so the restraints here were designed to not actually touch the listed structures, but to be supported off of the pontoon themselves, so that pile there, that spud leg, is actually supported inside the link float pontoon, and the blue restraint frame there is supported off of the basement of the foundation of the new building, the Newfoundland building, as it's being put up. And on the right hand side, you can see a very basic structural model for how the lateral forces are resisted by that restraint. And again, two of those restraints to maintain the position of that floating road. Next slide, thank you. These are then two photos that you can see on the left-hand side, an overview of the whole floating road system with the northern ramp there, the on-ramp, so to speak, just in the back of the page, and the Newfoundland building being built in the background. Again, the modular nature of these pontoons is essential for this particular project. It's not possible to get easy access into this dock area in Canary Wharf with a barge or a ship or anything of that nature, or any kind of a prefabricated large, pre-constructed large floating system. Whereas this modular link float system was ideal to deliver to the site and assemble in place. In a similar way that the link span bridges and the restraints were designed for similar kind of modular flexibility road transport. And on the right-hand side, you can see again the north ramp there, allowing for one of the vehicles turning on to the floating road, this HGV. Next slide, please. About link spans, ramps, also gangways. For the design for this particular project, again, constructability was extremely important. It was modular systems that were adopted and developed for the project. And one of the main reasons being historical issues with link spans and ramps on similar projects. Although, to be fair, not a temporary project, but a permanent works project, quite a famous unfortunate collapse, which resulted in fatality of, I think, 6 members of the public. But this was the Ramsgate Harbor collapse in 1994. So if you can follow that from the top right-hand side, this is a passenger ramp, access to a ferry, and it was the first section. So this was sort of 3 separate sections of ramp. The first section of ramp collapsed in service. Now the reasons for the collapse, following a significant investigation, the reasons for the collapse was identified some fatigue failures, basically due to motions of the seaward end of that first section of ramp. And effectively, what you have is quite a rigid, torsionally rigid structure, a sort of box structure in the middle there, which you can see that first section of ramp, very torsionally rigid. And the connection design down onto the pontoon did not allow for the motions of the pontoon. So there was a floating support pontoon, which was moving, perhaps not large movements, but frequent movements and twisting, and that over a period of months really caused failures of some of the joints there. And so as a result of this, significant improvements were made in the design recommendations for link spans, particularly around motion of floating link spans. And allowing for that motion either by designing for the high forces that can result if you make a torsionally rigid system, or to allow flexibility. So next slide, please. So given that the Canary Wharf floating road was to be in service for more than a year, and I think in reality it was in service for something like 2 years or more, to be fair, the decision was made at an early stage to allow for torsional flexibility and not rigidity, and to plan for sort of pin connections, which to a degree also help with the modular nature and allowed for the system to be fabricated offsite and then assembled on site. So a lot of pin connections and also flexible bearings. So in the plan view on the bottom right there, you can basically see 2 let's say longitudinal girders that are the main supports of the bridge in brown, and then between those girders in black and white, some let's say cross members, which are also rectangular hollow sections, but pinned to the longitudinal sections, and all of that allows for a certain amount of rotation. Those are two examples of bearing units are shown there in black and white. One of them at the upper end of the link bearings, allowing vertical rotation at the upper end of the system, and at the lower end down on the floating road itself, spherical bearings to allow for an element of rotation as well as translation. So again, flexibility to allow for movement. So next slide, please. And finally here, just an indication that for these temporary systems, it's also possible to consider permanent works design guidance. So in this case, some guidance from British Standard 6349 Part 8, and that's for the permanent works design of link spans, ramps, gangways. So on the left-hand side, an indication of potential widths that you might allow for in these systems, and in the bottom right there, some indication of gradients and ramps that are appropriate for roadways, passenger walkways and service walkways. Well, yeah, thank you very much. And the last thing I'd like to mention, just before passing it back to Chris, this particular project was also published in the Institution of Civil Engineers. So if you have a particular interest in it, there's an open access journal article that is freely available. And I think I'll get a link to that and pass it back to Chris and Stephen just to be sure, and perhaps that's something that can be shared after this. Thank you.
Thanks, Cliff. It was really interesting. Cheers. So there's number of interesting projects there, and different solutions for providing access over and onto water. If anyone has any questions on the system or any of the designs, we've got an open house now, so please feel free to dive in with your questions and comments. So. Got one from Kirsty Russell.
Hi guys, thank you
Hi.
very much for a really good talk and putting it into layman terms for people who aren't engineers. You mentioned the strength and the weight bearing loads really well. I'm just wondering, how much do you sort of allow for flooding events? Obviously you mentioned the movement with tides, but flooding events and debris coming downstream towards link floats, are there any sort of allowances made for that when you're putting these sort of structures together?
I think we've got somebody on from Harlan now, haven't we? We did talk about emergency mooring arrangements and serviceable mooring arrangements I think on the last call. So certainly if you're working in a river environment where you do have potential for high flows, then yes, you need to consider the potential loadings from debris coming down, but also from the high flows as well, you know. So you have a normal serviceable mooring system, but then you also have to consider what you do in emergency, you know. And it may be, certainly if you're working with a pontoon or barge, then you remove it and you take it to somewhere sheltered, you know, and then you berth it correctly and make sure that your moorings will withstand the forces, you know. In this area, certainly on the Union Canal, where it's navigable and there were vessels working, we had to consider collision damage from an 80-ton vessel. And that's why we considered the failure of the system, but also installed mooring chains in case there was potential for breakaway, you know. Whereas in Canary Wharf, that wasn't navigable. It was relatively sheltered water, and I think I mean Cliff will be able to comment further on that, but I don't think we had an emergency mooring system designed and installed in that example. Would that be right, Cliff?
Absolutely correct. Yeah, and I think as you mentioned, it's very much dependent on the specific system and the location that it's installed in, etc., as to what is allowed for. And yeah, absolutely. Cheers.
Yeah. Does that answer your question, Kirsty?
Yeah, that's great. Yeah. Thank you, guys.
And then we've got a question from Ethan, regarding tidal, managing tides. So in terms of, is that maybe some Cliff or Hamish can drop in terms of the tidal ranges in managing the various different heights and situations with the tides?
No, absolutely. If that's all right. I mean, I'd suggest that allowance for water level variation is very much similar to permanent structures. You know, so over the let's say over the design life of that temporary floating road, if it's a temporary one, albeit clearly some of these links floats have been used as permanent floating roads really in the past, or ongoing as well. But yeah, it's really no different from any pontoon type system. Yeah, in that basically you have to design the mooring. So for example, if the temporary Canary Wharf one is perhaps an example where you may have a spud leg being used on a restraint. And one of the things that we allowed for was a certain variation in water levels in the dock. Now, to be fair, it wasn't much. From memory, something like 750 mil, so something of that order, right? But still, you definitely want to make sure that there's enough range of movement from the top of the turret, that where the spud is being inserted into to the top of the spud leg, and that allows for full range of motion around the actual restraint. And that's the sort of, if you're using that kind of restraint system, then that's clearly the way forward. In terms of access, and let's say the ramps down onto and off of, that's another thing to consider. So for example, if you're following the guidance of 6349, so the British Standard for Maritime Structures, and you're following that sort of that suggestions around ramp gradients, which is actually rather good approach if you're looking at HGV access, which is quite often the case. Yeah, if you're following that sort of example, then what you might choose is let's say a typical range of motion with let's say favorable ramp gradients that are particularly favorable for the HGVs, and then you might also consider some extreme motions as well, whereby they're not as favorable for movement of HGVs, but they can still traffic it at say safe, slower speeds, and that's the kind of thing. So let's say slightly more extreme ramp gradients down and up for extreme range water levels, and then maybe more favorable ones for more typical water levels.
Yeah.
Yeah.
Hamish, do you want to add anything onto that?
Yeah, no, I think that was a good summary. I think in Maine as well, the big effect it has is a variation in bending moments and also the range capacity. So you've got the angles and everything to consider, as Cliff says, and then also where your pontoon is at the wrong. It's always the wrong height when it gets hit by a boat. So going back to the previous conversation, previous question, again during all of that, we assume worst state of the tide to put the biggest moments in when you're doing the collision design.
Yeah. And obviously you've got to consider location as well, because depending on where you are in the country and in the world, the tidal range is different, so you need to know what the conditions are at the location where the system's going to be moored, So yeah. Does that answer your question, Ethan?
Yes, it was. Thank you very much.
Thank you.
Thank you.
Do we have any more questions? Anybody want to chip in? Anybody got any questions from Hamish? I appreciate you missed out on the slides, Hamish. So Chris rattled through
Stephen.
them there. But yeah, does anybody have any questions on the Union Canal system? Yeah.
I didn't really spend much time on the design side of it, Hamish. I don't know if you want to just give a quick overview on your approach to the design there.
Yeah, of course. Yeah, I think with the design challenges really on that one, we're similar to I caught the last bit of Cliff's access, and access is always a challenge, and that's why the link float solution is fantastic. They have a big benefit of that one is the each of the link floats. I'm sure Chris and Stephen touched on it. Have 3 tanks inside them as well. So when we're considering the collision and damage stability, we always assume a sort of 2 compartments are damaged, but actually, when we're in a sort of 30 float system with 3 tanks in, 2 tanks is a very small percentage. So it allows for that extra resilience in the structure, as does the sort of the flexibility that the joints give you of not being completely rigid. That flexibility can help and can hinder you. And then in the main design of the link spans and the ramps as well, that was all designed to be fabricated in the VolkerMarine Services workshop and then delivered down to site in sort of road transportable and easily handleable pieces. So that takes that was a big part of the benefit. the most awkward shapes ended up being the what we were called the cheese wedges during the design phase that actually transition you from the full depth of the link span down onto the ramps and down onto the pontoon. Because it's not so much the gradients that get you, it's the variation in gradients that really gets you, and that's where you end up bottoming out or catching the back of trailers and their relative defence boards.
Excellent, thanks. We've got another question here from Mark Dawson. How do you consider the effects of high winds as well as tidal range?
I'll turn that on if you want, Cliff, or do you want to do it?
No, carry on. Yeah, absolutely.
No, unfortunately, the design codes and common practice is you have to assume everything's bad at the same time. Unfortunately, especially if you're in a sort of a coastal environment, normally the bad weather gives you a brief of actual tidal surges as well. So yeah, the wind would be to normally an installed limit. So we were looking at a 10-year return period at Grand Union, and if it was in for a longer period of time, you stick to the Eurocode, which is 100 or if not longer year return period winds. Does that answer the question?
Mark, has that answered your question? Yep, excellent, thank you. Anybody else got any questions? Here we go. We've got another one from Kirsty. So when considering loading of heavy plant onto a pontoon, depending on the position needed of the plant, such as a crane, how do you manage counterbalance and movement? So yeah, I mean, we talk about ballasting, dynamic ballasting. That's probably something for Hamish again. I think we did talk about it on the last call, but yeah.
Cranes in particular are a big challenge. As the crane slews around in its 360, each corner in turn wants to go lower in the water as the load or the ballast passes over it, depending on if the crane's loaded or not. And so when we're designing the link float pontoons, we ensure that you have enough stiffness in the roll and pitch directions to allow the crane not to go out of tolerance. And most crawler cranes work to 1 or 2 degrees of angle, and then most mobile cranes are more sensitive than that. So what we do is go into the owner's manuals of each of the pieces of equipment, understand the tilt sensor limits, and then from there we then ensure that the pontoon is stiff enough, which means it doesn't roll or pitch sufficiently to allow it to work.
So we can transfer water around the pontoon into the individual tanks within the units to counterbalance any loading, dynamic loading on the raft caused by lifting or movement of plant on the system. Yep.
Exactly, and the mass in the link float is nice and easy because each compartment is about 5 tons of volume, so it really helps us naval architects out, but counting in 5s.
Yeah. Does that answer your question, Kirsty?
It does, yeah. Thank you, guys.
Excellent. Any more for any more? I think we've exhausted that, so not. Well, thanks for your input, guys. Thanks for the Cliff and Hamish for their input today. It's been really interesting. Come up with some really incredible solutions, really, for some difficult problems. Certainly, I think the Canary Wharf scheme wouldn't have been constructed if the contractor hadn't been able to access the site from the water. And certainly, one of the piers on the Colne Valley Viaduct would be very difficult to access without the floating roadway that we've installed on the Union Canal. So interesting solutions to difficult problems there using the link float system. But if any of you guys are looking to access over water or float plant, certainly give Chris and the team a call, and you know, we can look to see if we can provide a solution using the pontoon systems. So no. Thanks for your time, guys. Got a few minutes extra on your lunch, so hopefully we'll see you again at the next Lunch and Learn. Thanks very much. Cheers now.
Thanks, everyone.
Right, cheers. Bye bye now. Thanks.
Thank you.
Thanks very
Thank
much.
you.
Cheers.